started. So thank you all for coming to the second session of the workshop today on NISQ and quantum simulation. Our first talk is going to be by Sophia Economou from Virginia Tech about efficient variational quantum eigensolvers for NISQ hardware.
Thank you. Thank you for the invitation and for organizing this nice workshop. So the work I'll talk to you about today is a collaboration between 4 of my postdocs shown here and 2 students, and some collaborators outside my group at Barnes, Nick Mayhall, and his student Harper. So since this is the first talk in this session, I'll give a little bit of an introduction. So I'll be concentrating on digital quantum simulation, which is different from Feynman's original vision, which was more focused on the idea of an analog simulation where you create a Hamiltonian of a system and you basically recreate the Hamiltonian of a system you're interested in on a controllable emulator with tunable parameters, and then you can study various physical phenomena. On the other hand, in digital quantum simulation, this is more like a quantum computing model where every evolution can be broken up into gates, and you use those gates to create a state that you're interested in and measure useful properties from it. And the prototypical problem we're interested in this field is simulating a many-body problem of fermions. So this is a fermionic Hamiltonian in first quantization. And the standard approach is to go to second quantization, where we choose some basis. The Coulomb integrals are all computed and shown here as parameters. And of course, we have creation and annihilation operators for the fermions. One important point is that while fermions obey Pauli exclusion principle, which translates to these anti-commutation relations for the fermionic operators, qubits are distinguishable, which means that somehow we need to impose the antisymmetrization of the wave function at the qubit level. And we do this by replacing creation and annihilation operators with not only ladder operations for the qubits or raising and lowering operators, but also with these operators multiplied or tensored with Z gates on all the qubits that are representing the orbitals prior, numbered prior to that particular orbital we're either creating or destroying a particle in. And this works out so that these relations hold. So in the end of the day, we pick a way to map. Here we focus on Jordan-Wegener, although most of what I'll talk about can be generalized to other transformations. And we transform the Hamiltonian to a sum of weighted Pauli terms, shown here, Pauli strings. The original way people envisioned solving many-body problems was doing the phase estimation algorithm, where you have to create the many-body state, and then you use an ancillary qubit or a set of ancillary qubits, and you do a conditional U operation, where U is just the exponentiated form of the Hamiltonian. And of course, that now, since this is an eigenstate, picks up a phase which includes the energy of that state. And then by doing measurements on the ancillar set of ancillas, we can recreate this energy here for measurements. So one tricky point here is that this conditional U is a many-body unitary, which means that to do it in terms of single and 2 qubit gates, we need to trotterize it. And of course, at the limit where n goes to infinity, this trotterization is exact. But in practice, that of course cannot be done. We have to stop at some finite order. So for example, exponentiating the hopping term looks like this. So it's a very large circuit, and it's outside the scope of what can be done now, or even in the next 1 or 2 years, if you're optimistic, with the hardware. So that's why we're interested in what's called NISQ, which takes the approach of we cannot do everything we'd like to do with a universal quantum computer. So what can we do with what we have? And there's hope that simulation of many body systems can be achieved with NISQ devices, although that's still a big question, of course. And we're focusing on hybrid classical quantum algorithms, because there you are not demanding, you're not putting all these demands on the quantum processor, but you're letting the classical processor help you run the algorithm. So this is a schematic of how variational quantum eigensolvers work. It's basically just the variational principle of quantum mechanics. The only difference is that now the state is created, it's encoded in a quantum processor rather than on your classical computer. And the measurements are also done, of course, on that state. And the results of the measurement are passed on to a classical computer, where the parameters that are used to create the state, shown here in this circuit, T of theta, are varied and optimized until we reach a point where the energy is minimized. And at that point, we decide that that is the ground state energy, or at least we have a bound on the ground state energy. So these are some recent highlights. You'll hear more in the next talk from the Google group, but there's been a lot of activity in showing proof of principle experiments where molecules that can be easily simulated on a classical computer are simulated on a quantum processor. This is still very interesting. The quantum processors are at the stage where they can do this, and there's a nice results from IBM, Google, and academic groups as well. So for my talk, I'm going to focus on the stage where you create the ansatz. That's going to be the focus for this work. And I'll start by talking about symmetry enforcing circuits in fermionic problems. So first, let's take a step back and think about what is the good ansatz. So you have an infinite number of ways you can create an ansatz. And of course, this is a crucial thing, because if you don't have an ansatz that includes the solution you're looking for, then of course that's not very useful. But you also have to worry about other things. For example, quantum coherence is still very limited, so you want to have shallow circuits. Classical optimization itself is not infinitely powerful, so you don't want to overdo it with too many optimization parameters. And you, of course, need to span the space where the solution lives. So right now, people are focusing mainly on two types of ansätze. So one is what is called hardware efficient, which is mainly random circuits, which are considered to be highly expressible, as we heard also in the previous talk, where you alternate an entangling gate with a general parametrized single qubit gates. And the issue with this one is that it's ad hoc. It's also inefficient in the sense that because these are very expressive circuits, they might be spanning more of the Hilbert space than you would want to. And then there's also the issue of barn plateaus for generic random circuits. On the other hand, you can have a physically motivated ansatz. And in particular, since most of my talk will focus on molecules, people are considering using chemically inspired ansatze, where you take the Hamiltonian and you look at the terms in the Hamiltonian, which are single and two-body terms, and you just create an exponential made of sum of those in the exponent with some weighted parameters, which are the parameters you optimize. So the issue here is that you need to translate these fermionic operators into an efficient circuit, which is a difficult problem because you go back to the issue of triptorization, which, since you're stopping now at finite order, it's not unique. And also we've shown that you don't always achieve what's called chemical accuracy. So there's issues with the two kind of main paradigms of ansatz that are considered for such problems, and that's what we are aiming to improve on. So our approach is to consider or to create problem-tailored ansatz, and I'll discuss about two approaches we have. One is imposing symmetries, and the other one is an algorithm we call adaptive EQE. So the features we're going for is we would like to have as shallow a circuit as possible. We don't want to overdo it with classical optimization parameters, and we'd like, of course, our ansatz to contain the exact solution. So in a nutshell, the kind of approach we're taking is you consider the full Hilbert space. Inside that Hilbert space, there's some symmetry sector where your solution lives. And within that is the state you're looking for, which is the ground state. So the first thing we consider is impose the relevant symmetries that you know your state has at the circuit level. So if you have n orbitals, that translates to n qubits. An arbitrary state requires 2 times 2 to the n minus 2 real parameters. But for a system of m fermions, so we're fixing the particle number here, the number of variational parameters you need is much smaller, is 2 times n choose m minus 2. So a key ingredient in this approach is this gate, which I'm writing it here in the 0.011011 basis. So in the middle block here, there is mixing because this preserves the number of excitations. So our solution was to consider as many gates of this sort as we need, which are parameterized, so that we only have this number of parameters, and we tile them in a way that you only need nearest neighbor gates. And we have proven by running numerics that this can span all possible states that have a fixed number of excitations. And then if you further impose time reversal symmetry, all you need is real states, so that reduces the number of parameters even less. So we've compared this to previous approaches, and we have shown that this approach minimizes the number of C-naughts. We also have a variation of this where we can also impose total spin, which is a little bit trickier. And we've compared our ansatz, which is this red dots here, with a built-in ansatz, which are these random circuits in Qiskit, IBM software. And we see here that ours has the smallest number of parameters, which it should, because this is by construction the case. But also, it happens to perform better and have a smaller number of C-naughts for this example, although this is not guaranteed. And we have also more results that I don't have time to show, where we put in noise and show that these perform reasonably well as well. So the next step we want to take is tailor the ansatz to the Hamiltonian even further. So far, we impose symmetries, so we can kind of look inside the sector S. But then one question you could ask is there a more organized way to go directly to this ground state from some initial starting point? So the way you could view this work is like in the most extreme, you have ad hoc ansatz which don't know anything about the Hamiltonian you're simulating or the solution, so they're very random. Then you can impose some symmetries, so you know something about the Hamiltonian or the solution. And then the algorithm I'll present right now kind of goes further in that direction, where you're tailoring the ansatz very much to the Hamiltonian under simulation. So basically, this approach allows the simulated system to dictate its own ansatz. And the ansatz is compact and it's grown iteratively, one operator at a time. So we use a pool of operators, which I'm going to talk a little bit more about later in the talk. And we consider exponentiating these operators to get unitaries, where I have here some parameter, optimization parameter. So here's a flowchart of the idea. You start with this operator pool. These are going to be forming the gates. And you start with some reference state. And then you ask, if I differentiate with respect to the parameter in the exponent, then which choice of these operators maximizes this gradient, the absolute value of this gradient. And it's easy to show that this is equal to the commutator of the Hamiltonian with that particular operator. So the next step is to choose the one that has the maximum gradient and act it on your solution or add it to your circuit. And then you might have converged according to some criterion. If not, you re-optimize all the previous parameters and you keep going. Then you keep that operator in the pool, so you never throw out any operators. And then you ask again, what's now the next, in the next step, what's the largest gradient? You add that one, and you keep going until you converge. And one important point is that this step here is quantum parallelizable. So you can imagine that you do each of these measurements, on a different quantum processor, so this would not cost you in terms of time. All right, so a crucial component of the adapt algorithm is the operator pool, which I have not told you yet how you choose. And the simplest thing you can do is kind of go back to the chemistry of many-body Hamiltonian and say, okay, these are the operators that appear in my Hamiltonian. I can start by using exponentiated form of those. And we call this Fermionic adapt. So the first thing we did is try simulations on our classical computer with this operator pool. And here we compare the exact solution. We can easily find it for these simple molecules, lithium hydride, beryllium hydride, and a chain of hydrogens. We compare that to the UCCSD, which is one of the first answers that I showed you, Hartree-Fock, which should not perform too well, and then adapt at different orders. And the different orders of adapt means how tight do I put this threshold condition from the previous slide, where ideally the gradient would go to 0 and that's when I stop, but in reality we just pick some threshold. So here in this scale, all of them but Hartree-Fock kind of look the same. So we plot the error, which means how far is the solution these algorithms found from the exact energy. And this shaded area here is what's called chemical accuracy, which is the area where chemists are happy if you reach. And you see that for the simple example, all of the algorithms, all of the ansatz actually do reach chemical accuracy. However, when I go to this more strongly correlated system, UCCSD fails, but the more stringent adapt ansatz actually succeed. So you can ask, at what expense do you succeed here? So how many variational parameters do the different ansatz contain? So here we plot the number of parameters in the ansatz as a function also of the distance, same x-axis. So the UCCSD is a fixed ansatz, so it's fixed throughout. But you see a very interesting feature here is that the adapt ansatz actually performs much better also in this criterion. So it almost always has much fewer parameters than what UCCSD has, except for the case here where you need more parameters, but this coincides actually with when UCCSD does not work very well. So here the extra parameters that adapt kind of demands are needed to achieve convergence to the exact energy. So one thing you could ask here is, okay, you're comparing to UCCSD, which is an exponentiated form of the sum of all these Pauli rings with some coefficient, which are single and double excitations. So one thing you could kind of complain about is that perhaps I'm kind of cheating, because by using product of such operators, maybe it's just a kind of artifact of essentially sneaking in higher order. Because if I were to reassemble this with Campbell-Baker relationships, then maybe I would get higher order terms that way. So to kind of address this point, we looked at other orderings of these operators. So instead of having the adapt criterion tell us which operator to choose, we just chose random operators, and also kind of ordered according to some criterion. And you see here that the adapt criterion always finds, we have tested this in other molecules and other bond distances, always finds kind of the path that takes you fastest to the ground state energy compared to everything else here. So this is not such an artifact. It seems to be really, extracting information of the Hamiltonian, and the Hamiltonian is kind of telling it where to go. So far, we're dealing still with fermionic operators. And these are tricky because now if I wanted to run this on a quantum computer, each fermionic operator would give me of the order of n gates. So I would still have to pay the price of deep circuits. So I'm kind of gaining in a number of parameters, but I still have to address this point of not going too far into deep circuits. So now we're changing the type of pool we have. I'm using a qubit pool, which means I'm not taking any inspiration from the fermionic side. I'm just using a pool of operators that's reasonable on the hardware. and specifically using this type of operators where P is a Pauli string, and we restricted it up to 4 Paulis in the string. So these are the results where we compare how does this version, the qubit version, perform compared to the fermionic version. So if I look at how fast I have convergence, so it's again the difference between the exact energy and what we find, you see that the fermionic one, which is the red, actually goes faster, converges faster, which means that you need fewer optimization parameters in that case. However, you could also now ask, how do my circuits look? How many C0s do I need in each of these two cases? And now you see that the one that is doing better in terms of optimization, number of optimization parameters, doing much worse in terms of C0s. And the simple reason is because I had all these operators bunched up in the exponent, and when I factorize them, I generate more C0s. So the qubit adapt actually performs much, much better, almost by an order of magnitude or more in some cases, compared to this fermionic adapt. And we even transpiled the fermionic adapt to give it an edge. So we were comparing there. So one question you could ask is, how big should this operator pool be, which I haven't talked much about at all. So the first thing we did for these four size polystrings is we basically chose every polystring that doesn't manifestly give the zero gradient. And this ended up being very large, more than 450 operators, which is probably more than you would want in a reasonable scenario. And what we tried is just take this pool and start chopping it up to see how does that affect convergence. So we start reducing it by a quarter, 1/16, and so on. And you see that it keeps performing well up to some point where now it cannot find the ground state. So you can ask what constitutes a complete pool. So what I need to include in this original pool, which is a crucial part of my algorithm, so that I guarantee convergence. So the criterion is the following. We take the operators of the pool and we form their commutators, along with their commutators, with the commutator of those and their commutators, etc., until we run out, until we don't get any new operators. And the complete pool is defined if we are capable of, if it's a pool that's capable of getting states that form a complete basis when I act on an arbitrary state C with each of these operators. So this we checked. So according to this criterion, we chose complete versus incomplete pools of different numbers of qubits. And we can show here that the complete pools converge, like we expect, the incomplete don't converge. So one issue is that doing this approach of the commutators is actually something that doesn't scale well. So we would want it to scale better because we don't want to have to do that step every time when we actually run a quantum algorithm. The other issue is that I want my pool to not be too large, even if I know it's complete, because then I need to pay the price of these parallel quantum measurements on different or possibly the same processor. So what we found is that there's a notion of minimal complete pools, and these are defined as small size pools which still give me, still satisfy the complete pool criterion. And we have proven that the scaling is just linear, which is a really nice result. It's basically as good as we could have hoped for. And we have also a constructive approach of creating minimal complete pools. And I don't have time to go in the proof, but it's in this paper, and it's due to my postdoc, Vlad Shkolnikov. All right, so with this, I kind of want to wrap up the fermionic discussion and just show you in a few slides before I finish the results we have for QAA, which is a quantum approximate optimization algorithm. So optimization problems can be encoded in Eigen Hamiltonians. This is an example of an optimization problem called max cut, where you have a graph and you want to find a cut such that you maximize the number of edges you cut. And this one, the problems like this, you can actually map them. For example, this one, when you form the cut, you can think of all the points on one side of the cut as being white and black, or you can think of them as being spins pointing up and spins pointing down. If you think about it that way, then you can form a cost function which looks like an Eigen Hamiltonian. And the idea is then that you want to minimize this Hamiltonian, which is equivalent to maximizing the cut in the original formulation of the problem. And there's this pretty well-known idea of a QAOA algorithm. It's a heuristic algorithm by Fermionic and collaborators, where the algorithm goes as follows. You start from an initial state where you put all the qubits in state plus, up plus down. And that's an eigenstate of this Hamiltonian, which is just the sum of x's. And then you create this QAOA ansatz, which has this alternating form. It has the problem Hamiltonian followed by the this mixture Hamiltonian, which is the original Hamiltonian, so to speak, and then you alternate them, and you have different optimization parameters as gammas and betas in the multiplying operators. And this is kind of inspired from the adiabatic theorem, because you can imagine that in an adiabatic formulation, this is your original Hamiltonian, and this is your final Hamiltonian, and you have some knob where you smoothly switch this one off and switch the other one on. And this algorithm, this ansatz very much looks like the trotterized form of that solution. So this set of operators here is called the mixer. And what we have done is ask, are these the best mixers you can have? So what we postulated is a different type of ansatz, where we preserve the QAOA ansatz structure. So we alternate the problem Hamiltonian with some mixers, but now we allow the mixers to be something else. And following the adapt strategy that I talked about before, we allow the problem to kind of call for its own mixers. So we define a mixer pool, which is given by these operators, single qubit operators and entangling operators, as shown here. And then we use the adapt criterion so that at every second, at every layer, we determine what the mixer should be. So we have simulated here what happens for different graphs. So we chose this 6 node graph, with different types of connections. So this has 3 neighbors. Here, everybody has 5 neighbors. And what we compared is the original QAOA ansatz, which is the blue curve, to the adapt QAOA, which is our approach, with either only single qubit gates, so different single qubit gates than the original QAOA, and also here allowing entangling gates inside our mixer pool. And you see that adapt with entangling gates performs much better and converges to the ground state energy much faster compared to either one of the 2 approaches, consistently in these 2 cases and for other problems we've tried. So one thing you could ask is, at what cost do you do that? Because my mixer now contains entangling gates, so perhaps you're paying a cost of more entanglement, in which case this improvement would not be surprising. However, what we found is actually you achieve high accuracy here with fewer C nodes, which I find a remarkable and surprising result. So if you look here at the parameter count, the adapt entangling mixer case has smaller number of parameters and smaller number of C nodes than either of the other 2. And this is consistent also for this graph.
Sophia, we're getting a little bit into the question
I'm actually at my summary.
Oh.
So yeah, this is a good time. So I presented 2 different kind of variational quantum algorithms. One is focusing on fermionic simulation, where we have introduced symmetry preserving circuits, and the other one is adapt VQE. And then I also talked about QAOA and the new idea of finding mixers through this adapt criterion, and all these papers are linked here in case you're interested.
Great. Yeah, thank you for the talk. So we have 15 minutes for questions. Please feel free to either raise your hand or speak up, or you can type your question into the chat and I can read them out loud. Just to start things off, I actually had a quick question about something that you I think mentioned a few times in the symmetry preserving circuit section of your talk, and also for the adapt QAOA. You mentioned the C0 count in the circuit many times. Is there a reason why you're specifically thinking about the C0 count as a measure of, instead of other two-bit gates? Why that's something you're tabulating? Or
No,
would that change significantly?
It wouldn't. We just use C0 because it's kind of the most commonly considered gates. If you look at specific platforms, of course, things might change a little bit. If you look at IBM, you might prefer to use cross resonance, but we just thought that this is a more universal way of comparing and quantifying. And of course, since we're still talking about NISQ, our currency is the 2-qubit gate and not T gates or anything like that.
Also, just a question about, you mentioned at the very beginning, phase estimation is in part difficult because you have to implement this conditional unitary operation, which you mentioned. But is there also a reason why phase estimation is more susceptible to noise and things like this than what you're considering, like VQE?
The nice thing about the VQE is because you're optimizing, some coherent errors could actually be taken care of by the variational nature of the algorithm. So, for example, if your gate, doesn't have the exact same theta in the exponent that you think it has, then the optimization loop could take care of that. So that's something. And actually, since you mentioned phase estimation, maybe I can also make a comment that the work I presented is actually also relevant for phase estimation, because in phase estimation, you still need to create the ground state. So that's a problem, or whatever state you're interested in. So that's still a non-trivial problem in the phase estimation case, which is not, it's not solved there entirely. So there are ideas on how to do it. So this VQE step could actually be a useful step, and I think will probably be a useful step for phase estimation as well, because you have to create the state.
Great, thanks. We have a few questions in the chat. Tianzi, maybe you can unmute yourself and go ahead.
Sure. Thank you. So I want to ask a simple question. So in your selection of tools, you have this E to the I Pauli operators. So I'm not sure. Is that easy to implement, or what is the criteria to choose or restrict these operators?
So you can, you would need to, in most platforms, you would need to decompose it into some circuit that probably contains C0 or other type of gate. The reason we chose that is that it's much easier to impose, to formulate the adapt criterion. So the nice thing about those is that you only have one optimization parameter. So then there's a very well-defined way where you can get, the gradient with respect to that parameter. Whereas if you had some more complicated thing, then it would be, it's not obvious how you could implement a simple criterion like the adapt. You can do something more complicated. You could ask, how much this operator lowered the energy, in which case you would have to do a full VQE per operator. So it would actually probably be too costly to do that. I don't know if I answered your question.
Okay. Yeah, I think you have shown benchmarks for performances if you use the restricted pool compared to the more comprehensive pool. And I think that test is only for 6 sites or larger system. There was a few larger.
So this was for, let me go back actually. Yeah, so these simulations are for 8, 12, and 12 qubits. So the number here, yeah, so the number of orbitals we keep are 8, 12, and 12. But that just, you know, it's just a large system that we could do classically. That's why we chose that. Probably if you use something more sophisticated, you could go higher, you know, and do a classical simulation of more. But qualitatively, we don't expect these results to really change.
I was thinking maybe only 6, but actually you have 12 qubits. For last panel.
Yeah, I think there's another question in the chat.
Yeah, Tom, you can go ahead and.
Yeah, sure. So I'll ask this. So thanks for the nice talk, by the way. So in your adapt strategy, you choose operators from the pool based on the gradient of the energy. And I was just wondering if that selection criterion is expected to work also for other cost functions besides the energy, or if you expect different cost functions to sort of necessitate different selection criteria.
No, this one should work. So long, I mean, you know, this is a very generic form that the Hamiltonian has. It's just a weighted sum of Pauli strings. So long as you have that form, which is pretty generic, then you can also use other cost functions, definitely.
I had a quick question, sort of maybe a bit more of a vague question, but for the QAOA, the motivation for QAOA, like you said, I think also is it looks like the trotterization of like the adiabatic Hamiltonian that you would use in the adiabatic algorithm. But is there, so in your adapt protocol, the operators that you end up choosing, is there a similar like physical picture that you get for what you're actually doing?
Yes, that's a very good question. And what we found recently is that you can connect that to shortcuts to adiabaticity, which is
to what? Sorry, could you say that again?
Shortcuts to adiabaticity. So there were some papers starting from Berry, I think around 10-ish years ago, where he showed that you can stay in the same adiabatic trajectory if you modify your Hamiltonian in a prescribed way, such that you actually trace the adiabatic path, but you don't have to go slow. So what we found is that actually that criterion gives us, we tested this numerically, gives us actually operators that would have been selected if I were to do some kind of shortcut to adiabaticity protocol. So I think there's a deep physical connection between that. You know, we haven't proven it entirely analytically, but we have a very, you know, very strong numerical evidence for that.
Since we have time, so can I ask another question? So the QAOA problem, can you elaborate more about what has been optimized and why do you choose the set of mixer in your algorithm?
So we tested it for an example of a simple problem, which is the max cut. It's a common problem, you know, to benchmark optimization algorithms, so that's why we focused on that. It also has a very simple form in terms of Eigen Hamiltonians. So basically here you're optimizing, you can view it as optimizing a classical Hamiltonian. So you want to find the ground state of this Hamiltonian, which of course you know will be a separable state of spins pointing up and down. And the idea is that, you know, at least in the original formulation, you can actually find the ground state of this Hamiltonian more easily or more efficiently, at least that's how it's postulated, by allowing the system to go into quantum states, even though you know that the real solution is the classical solution. And, you know, there's evidence for this. It's still an open question if this can beat, you know, anything classical. But the idea is that we go kind of maybe even deeper in a quantum state, so to speak, because we allow, you know, all these mixers to take us anywhere kind of the Hamiltonian tells the states to go, so to speak.
So what mixer did you choose?
So the mixers are actually chosen. So we give it this pool here, shown over here. And I had some plots, but I don't think I have them in the stock, where we show the frequency with which each mixer is chosen. And more often than not, a mixer different than the mixer of the original QAA is picked. So they have this form shown over here.
And the reason that it gets better performance compared to the previous result is is there an intuitive reason why?
Yeah, I think it's related to what I just mentioned about the giving shortcuts to the diabaticity trajectory. I think there's one or two more questions.
Yeah, there's. I think the person asking the question can unmute themselves if they'd like.
Yes, hello. Yeah, I was just wondering if, well, in this example of like optimization algorithm, you can only define a cut if you have a product state, but this Hamiltonian does not have a product state as a ground state. It will be a mixture, well, a superposition of different product states. So how can you...
The Hamiltonian C actually is classical Hamiltonian, just as Z's. So this one does have. So if you were to do, you know, exactly the diabatic, you would go to a product. Of course, all these algorithms that are heuristic, since they do create entanglement in the middle, presumably, you know, they might not necessarily go exactly to product state. They might go to something that has a very large component, which is your solution is a product state plus some small. But then measuring, you know, with very high probability, give you the product state you're looking for.
Another part of that would be what guarantees that it is a cut. It can be, you know, some closed loop, a collection of closed loop and similar.
I mean, cuts, we define that you don't want to cross more than once the edges. And then, you know, if you could view it like a closed loop in some sense, like you could view this one in the picture like a closed loop, right? Because the only point is that you leave some nodes on one side and the rest on the other side, and you don't want to cross again that same.
Okay.
Great. I think we're basically out of time for the question session. So Sophia, thank you for your talk.